Welcome to Lecture 10. We'll be discussing the launch vehicle designs. And so let's first start talking about Newton's law of motion. In essence, an object at rest tends to remain at rest. An object in motion will always tend to remain in motion. And for every action, there is an equal and opposite reaction. Newton's laws are within a more general principle called the conservation of momentum. And the momentum is mass times velocity. In a system that is not disturbed from outside, the total momentum stays constant. If velocity is zero, momentum will be zero. So that's Newton's first law. If velocity is not zero and mass does not change, then the velocity does not change. That's Newton's second law. And so here are the key principles that drive the behavior of launch vehicles, and each of them play an important role in that. Newton's first law of motion. So you typically will have thrust, drag, gravity, and then you'll have thrust is what will make the vehicle lift. A body in uniform motion remains in uniform motion, and a body at rest remains at rest. That's first Newton's law, again, unless acted by a non-zero net force. A launch vehicle will always stay at rest unless it's acted upon. And so the launch vehicle thrust has to overcome weight, gravity, and drag for liftoff to occur. Since the launch vehicle burns, mass is not constant. And so the rate at which the body's momentum changes is equal to the net force on the body. So that's F equals the change in momentum per time. And so clearly, the launch vehicle needs to ascend, and thrust plays a big role in that. So if mass changes, somehow the velocity does as well. If an object is initially stationary and a mass is projected, and says projected to the right, then the rest of the mass has to move in the opposite direction for the conservation of momentum. The projected mass has positive momentum, the rest has negative momentum, and the total momentum remains zero. That's Newton's third law, in essence. You can see here that I have 10 grams times 500 meters per second, and that gives me 5 kilograms per meter per second. And then in the opposite direction, I have 50 kilograms times 0.1 meter per second, which is 5 kilograms per meter times meter per second. So it's equal momentum. Newton's third law governs the behavior of launch and aircraft. The forward velocity is achieved by expelling exhaust gases at high speeds in the opposite direction. And while this vehicle expels mass away, the mass pushes back. That's third Newton's law. And so this is very important. So that expelling of the mass from the vehicle is basically akin to this situation. I have this, say this is a launch vehicle of the aircraft. This aircraft will move forward by expelling gas from behind. And so that is your third Newton's law. The forward velocity in this case is achieved by expelling those exhaust gases at high speeds in the opposite direction. Newton's third law governs the behavior of both launch vehicle and aircraft. And while the vehicle expels the mass away, then the mass pushes back. The difference between launch vehicle versus aircraft is quite significant. So in the first case, you have an aircraft who gets the oxygen for combustion from the atmosphere, and it does not operate outside of the Earth's atmosphere. The launch vehicle, however, carries the oxygen with it for combustion, and therefore can operate in space or in thin atmosphere. Rocket versus aircraft. So on the left-hand side, again, I have the mass that's stored in the vehicle and is expelled. And then we'll use a reaction force from this mass that's been expelled to propel the vehicle. All the fuel and oxidizer are carried. And then on the right-hand side, I have the aircraft. And the aircraft will capture the mass from the environment and expel it out. The reaction force is also caused here. And that reaction force, again, is from mass expelling back. And so then it propels the vehicle forward. In this case, we're using the fuel, which is carried on board. But now in this case, the air is found from the atmosphere. So you're getting that from the atmosphere, mixing with the fuel, and then making the reaction happen in the engines, which then will expel the mass for the vehicle to propel forward. And so continuing on, so let's look at the rocket physics. So I have the rocket physics. So here you have the pressure in the chamber, the temperature, and then you have the atmospheric pressure. This section here is called the combustion chamber. And here you have basically chemical energy that turns into thermal energy, that turns into kinetic energy. The nozzle expands, and so here you have the throat, and then here the pressure drops. And you have the cross-sectional area A here, and in essence, then you have the velocity of the mass expelled. And then so then the force due to this imbalance of pressure will give you m dot E times VE, which is the mass velocity, plus the difference in the exit pressure minus the atmospheric pressure. There's a difference between the two. And then times the AE, the exit area. Typically, the term on the right-hand side, this one here is fairly small. And so the force will then be equal to the mass expelled times the velocity of that mass. So the rocket physics, so then the thrust is really caused by ejecting stored mass, as you can see here, m dot, so the mass flow rate times the velocity. And so the propellants here in this case combine in the combustion chamber where it chemically reacts to form high temperature and pressure. The gases then accelerate and eject at high velocity through the nozzle, as you can see here, and imparts momentum to the engine. The thrust force is reaction force experienced by structure due to ejection of the high velocity matter. Then I have the aircraft engine physics. In this case, I have the chemical energy, the thermal energy, and the kinetic energy. In this case, in the aircraft, you have, again, the mass coming into the engine. Of course, you have a structural support from that wing. And then you have the flow velocity, the outside flow velocity, again, the exit area of that mass flow. And then you also have the mass flow m dot, which is the m dot of the expelled mass, the mass flow rate. And then U here is the flow velocity of the mass that's been getting expelled, but I'll call it VE. And then again here in the outside, you have the velocity of the aircraft and the atmospheric pressure. And so when you look at the force balance due to this situation, you get force equals m dot E, VE, minus m dot VO, V0. So the initial velocity of the flow into the engine, and then there's mass flow rate into the engine, plus PE minus PA again, where PE is the exit pressure and PA is the atmospheric pressure. These term tends to be fairly small, so you're left with m dot VE minus V naught, and so the flow through the engine is thrust, and fluid passes around the engine is drag, and is composed of the net change in momentum of the inlet and exit air. So this is what we got in this situation. And so from this equation, it is very clear that the required thrust can be obtained by designing the engine to produce either a high velocity jet of small mass flow or a low velocity jet of high mass flow. So you have two situations to create the required thrust. The propulsion efficiency is a measure of the effectiveness with which the propulsive duct of the engine is being used for propelling the aircraft. So the thrust is given by this equation here. And so the efficiency then is twice divided by 1 plus VE divided by V naught. And you can see here that if the exit velocity is equal to the initial velocity of the flow, then you get an efficiency of 1 or 100%. And so you definitely want to keep this as equal as you can, but that's impossible. The exit velocity will always be different from the initial velocity. So for rocket, this is the equation. The thrust is m dot VE. For the engine is the mass flow rate times VE minus V naught, where V is the exit velocity. And so here we have that again as a summary, the rocket, the propellant carries the fuel and oxidizer, which is why we have those stage tanks that are being used. And for the air breathing engine, is the fuel is carried on board while the air is found through the atmosphere and pulled in. Rockets usually require far higher thrust levels than airplanes. Airplanes usually fly for far greater durations than rockets. So rockets usually require far higher thrust levels than airplanes. Airplanes usually fly for far greater durations than rockets. So there needs to be a balance of the fuel, and there needs to be a balance of the oxygen that you need to create that combustion. So rockets will require far more thrust, and so that's why you need so much oxygen on board and fuel. So continuing on, I do want to discuss, it's quite important that the thrust calculation account for all the effects. So you have the weight and gravity and drag, and the thrust has to overcome these components of load. The thrust is in essence force times the mass flow rate times the exit velocity plus, and then you have the difference between exhaust pressure minus atmospheric pressure times the exit area. Or in addition to that, so that thrust calculation here needs to be greater than the weight plus gravity plus drag. So you definitely want to have a combustion process in that chamber that's quite significant to be able to give you the thrust that you need. The example of force that needs to be greater, that thrust needs to be greater than is drag. For example, drag is going to cause the vehicle to slow down. So you want a thrust to overcome drag, and that can be determined by the coefficient of drag times the gas density times the velocity of the vehicle squared divided by 2. So that's your dynamic pressure right there. PV squared divided by 2 is your dynamic pressure. And then A is the area. So CD is the drag coefficient. And so this calculation here gives you drag. The drag coefficient is typically found through wind tunnel testing. And so what you want to do is to make sure thrust overcomes gravity, weight, plus this drag calculation. The rocket mass times acceleration, ma, equals thrust minus drag. And in essence, you want to make sure that you have sufficient thrust to be able to overcome drag. Otherwise, the vehicle is going nowhere. Another point I want to make is that this equation you see here is very studied quite significantly in physics. That's Newton's law. So summation of forces is equal to ma, and that's exactly what we have here. Summation of forces, thrust minus drag, and that's equals ma, the mass times acceleration. The thrust calculation. So the force, thrust is the force which moves the rocket through air. Thrust is generated by the rocket engine through the reaction of the accelerating mass of the gas. So what we want to do first, the first step is to take this equation, and let me make sure you well understand this equation, because there are things going on here. You have the mass of the flow rate, the mass flow rate times the exit velocity. This right here is your momentum. As I discussed, when you shoot a gun or you shoot something, that's going to put a reaction force on your body, which will propel you in the opposite direction. Very similarly, that behavior occurs in an aircraft or a rocket. When you shoot mass from the behind the rocket, that nozzle, then that mass expanding from the rocket in the aft end is going to cause a forward motion of that rocket moving forward. So we're going to take this equation right here, and what I'm going to do, I'm going to take that equation divided by the mass flow rate. I'll take the thrust divided by the mass flow rate, and then I will get something called equivalent velocity. So this right here is the velocity of the exhaust plus the exhaust pressure minus the atmospheric pressure times the exit area divided by the mass flow rate. So if you take this equation right here, you'll make that equivalent, you'll make it equal to the equivalent velocity. And this equivalent velocity is very convenient and is used to determine the total impulse of a rocket, which is basically the average thrust time, the total time of firing. So for example, let's examine this carefully. Why is this equivalent velocity? So here you have VE, which is the velocity of the exhaust. So that's clearly units of meter per second or miles per hour. And then here you have the difference in the pressure. And right here, that gives you units of force. So pressure times area is force. And force divided by m dot gives you units of velocity. So clearly these units of velocity, and the equivalent velocity is going to be highly dependent on that velocity of the exhaust, and then how you design that exit plane area. The greater it is, the more velocity you have. And then m dot, which is the mass flow rate, and becomes quite important to get that right. So the total impulse is a big calculation in rocket engineering. In fact, this calculation here is used to determine which rocket is more efficient, as an example. In this case, we have that I'm looking at the impulse calculation. That's I equals the thrust times the time, the total firing time. If I want to calculate the exact firing time and calculate this impulse, what I want to do is integrate m dot VEQ, because you can see here F is m dot VEQ from, and we found that through this equation here at the top. So F equals m dot divided by m dot equals VEQ, which is equivalent velocity. Bring m dot to the other side of the equation, and then substitute the force, so that is m dot times VEQ. And you want to integrate this equation over the time that the rocket is firing. And then the delta t has been converted to dt as a differential time element. And when you integrate this, you notice that m dot dt is in essence mass. So mass of the propellant times the equivalent velocity gives you the impulse. So notice how the time dependency has gone away. ISP. So ISP now takes even further that information, and it's almost like an efficiency calculation. So you can have a lot of mass of propellant, you can have a lot of equivalent velocity, so that will give you a large impulse. But what is the point of having a large impulse if you can't really lift the weight of the vehicle? So what the specific impulse then does is to take the impulse divided by the weight. And so your impulse is mass times equivalent velocity, and then the weight is m over g. So the lighter the weight of the rocket, and the greater the mass of the propellant times the the equivalent velocity, then the greater your ISP is, and the greater the ISP is, the greater efficiency of that rocket is. Notice how W, the weight, is mass times the gravity, and so mass cancels out, and all I get is the equivalent velocity divided by gravity. And you can notice how the mass dependence went away quickly, which is very strange to see that, because what are we trying to say here is, what we're trying to say is that the equivalent velocity, you want to be that to be greater than the gravitational forces. Otherwise, then the ISP will be lower, and you want a high ISP to get great performance. As you can see here, the units of ISP is seconds, which is very strange, but it does provide a lot of information about the rocket itself. So V equivalent divided by G, and notice how this is also F over M dot G, because this top M times V equivalent is force, thrust. And so in essence, this equation is what you get. And so ISP is a ratio of the thrust produced to the weight flow rate of the propellants. The specific impulse allows determining the thrust of the rocket by just knowing the weight flow rate through the nozzle. It provides indication of engine efficiency. Higher values of the specific impulse is more efficient because it produces even more thrust for the same propellant. So having the same propellant, having higher ISP is better, and you'll be working through some of that. It allows us to size an engine during preliminary analysis, and it can help you kind of determined to see if you have the right engine size for the application that you have in question. So now I can now use second Newton's law. So we talked about how force equals the mass flow rate times the equivalent velocity, and that has to be equal to the change in momentum. So I have D equals mass of the launch vehicle times the velocity of the launch vehicle dt, and that could be changing over time. And here I'll use the product rule differentiation. So I have D mass of the launch vehicle dt, velocity of the launch vehicle plus mass of the launch vehicle times the velocity, the rate of change of the velocity of the launch vehicle. And what we notice here is that if I place myself on the vehicle itself, then the velocity of the vehicle is zero. I could do that by assuming I'm moving with the vehicle. And that's a trick because you can always take a reference that's arbitrary. And what you can, so we'll continue. We'll continue here. The launch vehicle mass then is the inert mass, which is the mass that does not, is just structural mass. And then you have the payload mass, which is what you're trying to deliver to orbit. Then you have the propellant mass, which is changing over time because you're losing propellant, of course, because you're expelling propellant out. And so the only two things are constant is the structural mass and the payload mass. And then you have the rate of change of the velocity of the launch vehicle. And then what you have now is that this is equal to the mass flow rate times the equivalent velocity. So all I've done so far is to look at the equations that I discussed earlier, but putting them in a different way. And so now I want to continue working on this because there's something going on that's quite interesting. I can now study the mass of the launch vehicle. And I know it reduces over time because as I am ascending to space, the propellant mass is getting used. This MP is getting used. So it will get expanded fully until it becomes the inert mass. As a consequence, at time equals t, this is the payload mass times inert mass plus propellant mass as a function of time. The launch vehicle at time equals t, 0, is going to be the payload mass plus the inert mass plus the initial propellant that you have in the vehicle. The final mass, however, of the propellant is going to be MLV equals the payload mass plus inert mass plus the final propellant mass at T equals T final. And so when you look at what M dot is, M dot LV, so the derivative mass times with respect to time is going to be equal in essence to the derivative of mass with respect to propellant. And so that's good news because then I have this equation here at the bottom. So basically these are constant. This does not depend on time. Payload and the inert masses don't change as a function of time. So therefore, the derivative of this left side is equal to the derivative of the right-hand side. And so the mass flow rate is equal to m dot LV as a function of time. And so what I can do then, I can use this relationship. And I can use that relationship by plugging in what this is into the next equation. So m dot p is the launch vehicle, this one right here. So I'll substitute it right here. And so everything will be terms of m LV. And so here's what I got. That's the equation I got. And now what I can do is divide, bring dt to the right-hand side of the equation, and then I'll isolate dvLV. And so now I have this. Now what I can do is to notice. So notice how this multiplication m dot LVT dt, that multiplication becomes just dmLV. And so that's fairly straightforward. This times dt is just dmLV. And so I get this equation here equal to the left-hand side. And so now I can integrate this equation to then get the change in velocity of the launch vehicle, which is equal. And notice how the integral of this equation here is logarithmic, natural log of MLV. V equivalent And so now the integrals go from the payload mass plus the inert mass plus the propellant mass. And the final mass is not going to have any propellant because the propellant has been expanded. So the integral goes from this point to this point. And when you integrate all of these, you get that the change in velocity of the launch vehicle equals to the mass, propellant mass, plus the inert mass, plus the payload mass divided by inert mass plus propellant payload mass. And so you can see here this logarithmic here. And notice if I had no propellant, then this is 1, and you get 0 for change in velocity, which makes total sense. I need propellant to make this work. You definitely want to have as much propellant as you can to make this vehicle work. And so notice how this becomes MR. This right here is called the propellant mass ratio. So I call that MR. And so then the change in velocity of the launch vehicle equals to the log, the natural log of the propellant mass ratio times the equivalent velocity. So very, very, very interesting ideas here. Notice how I definitely need a lot of propellant mass to make this work and achieve the right orbit. So right there, that's a rocket equation. That's called the rocket equation. I am also showing it here in terms of specific impulse, the change in launch vehicle velocity equals the natural log of the propellant mass ratio times the equivalent velocity. And remember how the equivalent velocity was the ISP times G. So what I've done is use this equation right here, and feel free to pause the video to kind of remember this, but ISP is VQ divided by G. And so I'll basically use that equation to then write this right here. And so if I know the ISP of the vehicle and I know the propellant mass ratio, then I can calculate the velocity sensed by the payload and the velocity gain imparted by the system. I highly recommend reading the NASA article posted here, the propellant mass fraction calculation methodology for launch vehicles and applications to the Ares vehicle is provided. And in here you will see that they compare candidate launch vehicle designs and they show the various methods used in industry to determine the propellant mass fraction. They look at also at propellant mass versus dry mass, and they look at the idea of residuals, and they also calculate basically they provide a historical comparison between launch vehicle on the basis of differing calculation methodologies, and it is a great equation. This is the ideal rocket equation, and here you can see the maximum velocity of the vehicle, and then here you have the mass ratio, 1 over AMR. You can see how with increasing mass ratio that your maximum velocity increases. And as the impulse increases, specific impulse increases, then your velocity is even higher. On the left-hand side, you see here the feet per second. On the right-hand side is meters per second. And so notice how this ratio becomes important in the ISP to be able to determine the maximum velocity of the vehicle. So the delta V for various trajectories is quite important. If you want to go to the low Earth orbit, you're looking at needing 7,750 meters per second. If you're looking at just gravity and drag during ascent through the atmosphere, 1,400. If you're going to a flight path correction from vertical to horizontal, very little. If you're on launch to GEO and you want 10,200 meters per second, the lunar impact, if you want to land on the moon softly, you will need about 15,000 meters per second for delta V. Launching to lunar orbit requires less, that's 13,500. And then if I want to go to Mars, you definitely need and land and return that we're talking about there 23,000 to 27,000. To Venus, 23,000, 25,000. And then to the sun, 30,000. And to escape the Earth, 12,700. And to escape the solar system, 17,500 meters per second. And then if you want to continue on here, Here's the Atlas V 400 series launch system. This was extracted from the Atlas V user's guide. And you can see here thrust is provided, but ISP is also provided. So you can see how ISP is an important spec in engine information. Here you have the side rocket motor. The vacuum ISP is 279. So all this information is typically provided in the user's manual of the launch vehicle. The Atlas booster, here you can see again, the RD-180 has an ISP of 311 and in vacuum 337. You typically see these values given in vacuum and non-vacuum conditions. The common center, you can see the SP is 450, which is quite efficient for an engine compared to these other two that you saw. The typical payload ratio to low Earth orbit, you can see the various values here, typically in the range of 10% to 20, 30%. I apologize, I meant from 1% to 3%. And in essence, those are the ranges. We want to then look at payload fraction. It's quite nice to see that information. So look at the Ariane 5, we're looking at 2.5% payload fraction. The SpaceX Starship is 5.3%, and then the SpaceX Starship with payload alone is 3.4%. The Russian rockets is in the 2.6%, and the space shuttle was near 6%. And I can go on and on and on, but I do want to compare this to airplanes. An airplane, a Boeing 747, has a payload fraction 50%. And so, yeah, you can see here the difference is that a launch vehicle is primarily propellant mass. I mean, it's going to have a large amount of propellant. And that is not the case with airplanes, as an example. And so, continuing on here, let's look at structural efficiency so let's continue here. So we have the propellant mass fraction. And so E measures the structural efficiency of the system. And that's equal to the propellant mass divided by propellant mass plus inert mass. The propellant mass is a useful propellant, and that is which is burned to provide the acceleration in the desired direction. The inert mass is the sum of all the inert masses. And what I mean with that is a structural component. So, for example, the engines, the tanks, the pumps, the liners, the reactors, the propellant bottles, the gas generator, the insulation, all the electrical connection, all the construction of the rocket, that's the inert mass. And it's called inert mass because it's not expended. Only the propellant is expended. And so the best possible design in this sense will be consumable rocket that's made entirely from the propellant. In general, as you increase E with system size, then you get much higher structural efficiency. For given mass, the greatest possible delta V occurs when the payload is 0. So we will not want to have any payload that will give you the greatest delta V. Maximize the amount of payload while keeping the structural weight to minimum gives you the greatest efficiency. For mass of load-bearing structure, like rocket motors, pumps, pipings, you cannot really make it arbitrarily small. Current technology has shown that the lower you can get is 10%. So if you take the inert mass will be, you cannot go lower than 10%. If you do, you can, but you're going to require new technologies. And propellant mass is typically 90%, inert mass 10%. That's really optimal right there. Here, I'm going to take the ideal rocket equation, which is right here, and I'm going to add a few more terms. The extra terms is that the fact of the matter is that the velocity sensed by the payload will be decreased by 2 factors: drag as you travel through the atmosphere, and notice how when you travel through the atmosphere becomes thinner, and so drag becomes less. However, you do have gravity that's pulling back on you, and so that there's gravitational losses due to that. And so TB is a time for the burn to occur allowed to burn, and so that gravity times the time for the burn is going to decrease the vehicle velocity sensed by the payload. The fundamental expression used in rocket design links mission requirements, delta V, propulsion system performance, ISP, vehicle masses, which is basically the mass propellant ratio that we talked about. So these three parameters are of extreme importance. And to attain low Earth orbit, delta V requires 25,000 feet per second, but the drag and gravity losses are near 5,000 feet per second. So the propulsion system has to be able to provide more. There are some design traits that need to be considered. The best system will have both high ISP and high propellant mass ratio. However, think about it, it does work against each other. Hot propellant gives you good ISP, but then you require a lot more insulation, which will lower the mass propellant ratio. Large nozzle gives you really good ISP, but also reduces the mass propellant ratio. But high pressure gives you better ISP, but require thicker wall structures. That is a problem. And so you're competing these factors together, which these competing factors don't allow you to make as much progress as you would like. Here you can see the propellant mass required to accelerate 1 pound of payload with a structural efficiency of 90%, which is a more common value. What you see here is a delta V of an amount that goes up to 30. So 30 here, 30,000 feet per second. And then on the y-axis, you see propellant mass. You can see here that the greater the propellant mass, the delta V goes higher. And the ISP, in fact, the ISP calculations here show you the impacts on the delta V. So for example, for a given propellant mass ratio, say 10 pounds, I come here, and you can see how at 300 seconds of ISP, I only get 20,000. But if I go to a higher ISP, I can have even a higher delta V. Here's an example of common first stages going from the Proton, the Russian vehicles, Europeans, the American ones, and you can see here the typical ISPs. And the Orion has one of the best ISPs, and you can see here the inert mass is in the 6% to 10% for the Proton, the Russian vehicle. And so continuing on here, the inert mass fraction again is the gross mass minus the propellant mass divided by gross mass. So clearly I'm taking the propellant mass out and showing you what is going on with the inert mass fraction. Here, what I want to show you is a mass summary for current space propulsion side rocket motors. And you can see here that the propellant typically has a lot of weight. It contains the most weight typically. And the propellant mass is about 80 to 90% of the whole vehicle, with the majority of it going to the case and the nozzle. The other components tend to be of less mass. So moving on to launch vehicles and understanding a little bit more about the sizing process, you have here the payload, the third stage, the second stage, and the first stage. And here you have the boosters, the side rocket motors. And in the first configuration on the left, we call this serial staging. On the right-hand side, I'm showing parallel staging because the boosters are worked in parallel with the core. And so these two standard forms of staging are quite used in industry. In serial staging, the stages are stacked vertically in the rocket and fired one after another, while in the parallel staging, you're using stages strapped alongside each other, which are fired simultaneously. For example, take a Delta IV engine, Delta IV heavy design, the core and the core boost and the side booster called strap-ons, those together will be a parallel staging situation. These strap-ons can be sized very carefully to provide the maximum performance. So looking at staging, there's multiple stages permit us to drop some inert mass midway. That's a benefit there. So the benefit there is if you have multi-stages, you can drop a stage and then reduce inert mass. That's a benefit. You drop it out and then now you have less mass that you're carrying. That allows even higher delta V missions such as space access at the expense of development of more stages. And so detailed sizing studies generally look like this. So in the y-axis, you have the gross lift off weight below. In the x-axis, we have the delta V. And so if I have a stage one, what I want to do is plot these things together. So stage one is this one, stage three is this one, stage two is this one. You can then determine where everything crosses. And you can see I'm getting more delta V. So if I just have stage one, this is all I can get for delta V. But if I have stage two, then I can get this curve here. And so now I have added more delta V by adding more stages. Continue. So let's continue on here. So what is the sizing process for stages? Sizing process for stage vehicle. This process allows to size individual stages and the entire vehicle. Step number one, you want to choose the number of stages, and then you want to choose the minimum number of stages that is practical. You don't want to have too many stages necessarily. Choose different values for the number of stages and compare the marginal differences when it comes to delta V. We then want to choose the propellants very carefully for each stage, and then these traits can be then looked at very carefully. You know, if you want to start a rocket motor or another liquid rocket engine. And then you want to choose an inert mass fraction you want to shoot for. And we already talked to you about, you know, shooting in the neighborhood of 10% if you can. And then you want to allocate the delta V for each of the stages. And when you do that, that delta V allows you to better understand what total delta V you will get. Then you will size the stages in the vehicle. You will start with the uppermost stage and work backwards to the first stage. The payload for each succeeding stage includes the previous stages and the actual payload of the mission. So when you're looking at say you're looking at stage one, then the payload for stage one is really stage two. Say it's a two-stage system, then stage one will have the payload as stage two plus the payload. Stage two will only have the payload. So that's how you look at that when you're sizing the vehicle. Minimize the vehicle mass by optimizing its delta V fraction allotted to each stage. So you have to vary one stage, number one, to nth stage to determine the combination that minimizes the vehicle initial mass. It usually requires a numerical optimization technique and repeat the steps 4 to 5 to really find the minimal mass that you need to get to delta V. Here's an example of how you'll treat multiple stages. Delta V of the vehicle equals to stage 1 delta V plus stage 2 delta V2. You can see here how we're using the rocket equation, and here I'm using the ideal version. ISP for stage 1, G naught is known, ISP for stage 2, so you need to know the ISPs you're trying to target. And then in the denominator, you're going to have the payload mass. And then you're going to have basically the inert mass. And then in the top, you can see here payload mass plus inert mass plus propellant mass. And so that's your mass propellant ratio right here. Here you have payload 2, and then this is not for the second stage. And so what you want to do is work through these equations to determine the delta V that you need. Note that for the first stage, the second stage becomes a payload. Let me point you to a great paper by NASA on launch vehicle mass estimation relationship database. It was written by the Bobby brothers. It was submitted to Emory Lynn, and it contains a number of empirical equations to estimate mass of a vehicle, which is quite important when you're designing a rocket. So we can look at sizing a single stage. So for if you want to go to the moon, like a fly-by mission, just go by it. A delta V of 12,500 meters per second is sufficient. You can use a LOX, an oxygen hydrogen propulsion system with an ISP of 435 seconds, and then it will have a final mass of 1.81 times 10 to the sixth kilograms. The payload mass is 8,600 kilograms, and so then you can use this information somehow to calculate the empty mass of the vehicle and the propellant mass of the vehicle to achieve this. So the propellant mass accounts for 94% of the total mass, and the payload mass accounts for 0.5%, while the vehicle propellant is about 99.5%. So this is quite straightforward. If you were to have a staging example, and you have E, the structural efficiency is 91%, for stage one, the stage two is 89%, and I have LOX and fuel, so RP1 is a fuel, LOX and hydrogen is 89%, with the ISP given here of 300 seconds and 450 seconds for stage two. We want to deliver 50,000 pounds to low Earth orbit with an ideal delta V of 30,000 feet per second. So you want to assume the way typically people do this, they will split delta V across two stages, 15,000 feet per second here, 15,000 seconds, 15,000 feet per second here. So I apologize for that. We find then, if you do the calculations, that the mass of the payload is only 3.5% of the gross liftoff weight. So we're almost concluding lecture. I want to be focused. Pause the video here. Try to see if you can get the answers I got here. Again, divide delta V into two stages, stage one, stage two. Again, if you want to go to the low Earth orbit where the International Space Station is at, then you will split it this way. And then again, 90% structural efficiency. With this information, it's very easy to find the different masses that are calculated here. So I challenge you to kind of pause the video and see if you can use the rocket equation to get there. Very easy equation to use. So the sizing process. So you start with the mission requirements, whether you want to go to Mars, Venus, the Sun, or if you want to go interplanetary to another places. But these are the inputs to determining what vehicle sizing I need, what propulsion and options designs I have, what layout and surface geometry I need, and the weights that I need for the various components. Then you want to go into aerodynamic analysis, and that aerodynamic analysis is going to include a trajectory analysis. Structures control and thermal analysis are performed in conjunction, and then you'll then determine the vehicle configuration, dimensions, and steering rate history. I invite you to pause the video and download this particular article, which is called a multidisciplinary design optimization strategy in the multi-stage launch vehicle conceptual design. Here's a more comprehensive calculation for the sizing process. You start with the orbit specs, and then you calculate delta V total, and you want to allocate some to stage one and stage two. And remember that there are some losses for delta V associated with the drag and the gravity. When you put this together, you initialize this value of delta V, and then you calculate the ideal velocities. You choose a propulsion system that gives you an ISP for stage one and stage two, and then you want to vary stage one and stage two. And then you plug it in here to determine the liftoff weight and the different mass allocations you need. You want to calculate, basically size the tanks, estimate the weight, and then calculate the minimum low liftoff weight you need. And you want to keep iterating here to minimize that value. So liquid rocket engines, again, advantage, high ISP, start, stop, restart, ability to throttle. Disadvantages, complex. It uses turbo pumps or gas, lower thrust than solid systems, lower density storage than solids, and a solid rocket motor, which is essentially a bazooka that has high density, can be used. The disadvantage of liquid rocket engines is that it's toxic and we use cryogenic fuels and oxidizers. Solid rocket motors, in the other sense, are simple, have high thrust, are easily storable, high density ISP. Disadvantages is that in some cases you will have lower ISP than liquids, complex throttling, difficult to stop and restart. So once you have a failure, it's gonna blow up. It's very hard to stop it. And the disadvantage again is safety because the propellants tend to be toxic for the human body. Spacecraft may require thrusters to maintain orbit, and fuel may be needed to add it for attitude control to correct for atmospheric drag, lunar, and solar gravity. Once below 200 kilometers, atmospheric braking leads to reentry. Some spacecraft are positioned in the geo orbit to achieve constant position above Earth. If a satellite is launched at a point 36,000 kilometers above the equator, it will orbit the Earth once every 24 hours and appear stationary to an observer on the ground. So these satellites are very powerful because from the point of the observer on the ground, it looks like if you're 36,000 feet above the equator, that that object is stationary to us. And so that can be used for a lot of different things, like GPS and things like that. Spacecraft can weigh in excess of 20,000 pounds, and it can take a large launch vehicle to lift that. So launch to geo orbit, it is normal for launch vehicles like the Ariane 5 to have 3 stages, and for each stages to be dropped as propellant is consumed. The first stage uses a single powerful engine, which is called a volcane. The heavy lift rockets like the Ariane 5 have 2 or more rocket motors that will help lift heavier satellites. The solid rocket motor are jettisoned about 2 minutes into the flight. Typically, that's when the fuel has been expended. So you can jettison the solid rocket motors, get rid of that because that's extra weight you don't need. And so that'll help you really achieve the velocities you need. Typically, you burn it out about 60 kilometers above Earth. About 8 minutes into flight, the first stage has consumed usually all the fuel. And then the delta V here, now you're 2 kilometers per second. The solid rocket motors have been burnt out. The first stage burns out, and then that's about 8 minutes typically. That's at an altitude of 200 kilometers, and now the velocity is even higher, has tripled. So you want to get rid of that extra mass. Now you go into the payload portion, which is protected by the aerodynamic fairing. And again, this is not needed when the rocket is in space, so it's also jettisoned. We don't need that. So again, more mass, less mass, and you can get farther where you need. You can see here the second stage burns out now at 25 minutes at an altitude of 550 kilometers. The velocity is now 9.5 kilometers per second. That's step number 5. And so now again, I don't need all that material that's in excess because the fuel has been consumed. So now I'm ready to use my third stage, which is now ignited, and it burns until the correct velocity has been achieved. At this time, you shut it down. Now the satellite has enough speed to coast to a 36,000 kilometer altitude, which is the highest point of the flight. And this highest point is called apogee. Here's an example of the launch vehicle, which is needed to accelerate a satellite to a horizontal velocity of 10.3 kilometers per second and an altitude of 500 kilometers. This will put the satellite in an elliptical geostationary transfer orbit, and then this will then coast up to this geo orbit at 36,000 kilometers altitude. Gravity slows down the satellite until it travels only at 1.6 kilometers per second. The satellite will complete several orbits at that location while electronic systems are powered up. At the highest point called apogee, the satellite fires its own rocket motor called the apogee boost motor. The ABM accelerates the satellite from 1.6 to 3.1, putting the satellite in a perfectly circular orbit above Earth, which is perfect because it will be stationary at an observer from Earth to perform its functions for spacecraft performance for the Earth. that's needed. I want you to pause the video, read the problem statement here. This is Space Shuttle Columbia, which the engine ejects a mass of about 30 kilograms per second with an exhaust velocity at 31 to 3,100 meters per second. The pressure at the nozzle exit is 5 kilopascal, and the exit area is 0.7 meters per second. Sorry, meters squared. The mass of the shuttle solids is about 500 kilograms, and the question is to find the acceleration of the rocket. Why don't pause the video and figure out if you can make it work? My goal in this particular lecture is not to go through the solution. I want you to kind of think through it, use the formulas we discussed, and see if you can get to the answer. So here's what's given. Pause the video to write it out for, write this, see if you can get it. And then here's the calculation I've performed, see if you can get it right. I won't again discuss this because all the equations were provided. It's a simple plug and play. And I think you guys are senior in graduate school enough to really know how to use some mathematics here. So the important thing is to understand the physics. Again, conservation of momentum is required to fly a rocket. Here are beautiful 5, 6 rockets, very beautiful here. You can see here the Delta IV rocket. You can see here another beautiful rocket, that's the Atlas rocket. And these rockets are fully operational. Here you can see the Delta II rocket, which has been fully retired. And these rockets will then take people to either space, potentially, or to deliver spacecraft. If you listen to XM radio, use GPS or navigation or anything like that, these rockets made it possible. There are launch vehicles. They started from the Gemini Titan II, 1965, the first space shuttle, 1981, a beautiful rocket that sent people to space. You have the Titan IV, the Delta IV, beautiful rockets, Atlas V, the Falcon 9. And here I'm going to go through a series of example rockets. Here you have the Titan IV, the cost of them, and then the fuel weight and the thrust that delivered. Looking at thrust divided by weight can help to kind of see what's going on in terms of how much thrust I can produce, but ISP really gives the information you need. Typically, this thrust to weight ratio will be in the 1/10, about 10 times greater in thrust than weight. You will see that very often. The Delta II here, 60 million, and then the Atlas family of launch vehicles has evolved over time, and then you have here several Atlas V vehicles shown with the Delta V's as well. And then the Delta IV, the Delta family of launch vehicles is here, shown here. That's a heavy rocket. And these were the GEM style rocket motors. The Delta IV is a fairly significant massive structure that can carry payload to space up to 25,800 kilograms to a geostationary transfer orbit. Here's the Orion 44L, again a ratio about 10 there. Cost is $110 million. And then here's the Orion 520 million. The H2 Japanese rocket is about $180 million. Again, a ratio of thrust to fuel weight of about a 10. You can see the cost per kilogram, very expensive. Every rocket is very expensive. Chinese have a great rocket as well in the $50 million range with a 10-to-1 ratio of thrust to weight. Here's a sea launch. This one is launched from the sea. This is called the sea launch Zenit rocket. It's approximately 200 feet high, and it can basically deploy a spacecraft of 6,000 kilograms to the geosynchronous transfer orbit. I apologize. The Proton family of launch vehicle is shown here, and the Proton vehicle is a Russian vehicle. It's about $70 million, and again, a thrust to fuel weight not very far from the 10-to-1 ratio again. And this was very cool. Let me show it again. The rocket right there, the Proton rocket with several rocket motors. And then now again, beautiful rocket, very heavy rocket. I showed you that earlier by showing you the efficiency. The Soyuz rocket has been used by NASA and Russia United States and Russia to get to the International Space Station. And we're looking at a much later evolution of this, but you can see it here. And the specific impulse they're pretty good. The Energia rocket, again, over close to billions, what people believe, very expensive rocket. And the thrust to weight ratio not too far from the 10-to-1 again. The Buran Russian rocket looks exactly the space shuttle rocket. And in this rocket, and so this one is one of them. The only launch was November 15, 1988. The Falcon 9 rocket is shown here. You can see several evolutions of that. And with that said, I want to thank you for listening to me. And I apologize for posting this today. I will be posting a new video next Sunday. I hope you have a great rest of your day, and you please stay safe, but also enjoy your life. Remember, life is a journey, and it is important you stay active, mentally in it, and understand that we're going to all achieve something great, but you have to put your mind in it. So with that said, I hope you learned how rockets work and the differences between a rocket and an airplane. In the next lectures, I'll be discussing more specifically how to design a launch vehicle. And from there, I'll be discussing how an airplane is designed. But the ideas are very similar and the concepts are basically fundamental to both. So you have a great day.